So now you have I hope, a relatively strong understanding of how we lime acid soils in general, but to remove hydrogen, aluminum, and potentially iron from exchange sites, to remove the buffer. That's why we lime. So now let's talk about how to evaluate a potential liming source. And an effective liming material has to both neutralize acids as well as do something else called increase the base saturation. And what is meant by that? The base saturation is the amount of basic cations on the exchange sites of clays. Those basic cations are calcium, magnesium, potassium, sometimes sodium. All right. We know that sodium is not needed for plants. So we'll take that away for the time being. So calcium, magnesium, and potassium. Now, when we use liming materials, we often, in fact, I don't know anyone who uses a potassium source for a liming material. So let's nix this for the time being. So we use either a calcium source or a magnesium source or a combination of both. And that's what you see on this slide, roughly speaking. So how do we evaluate different liming materials, and are they good as liming materials for removing hydrogen, aluminum, and iron from the cation exchange sites, replace those cations with basic cations, in this case, calcium and magnesium? So how do we evaluate this? So let me show you three examples. The first example is calcium carbonate. And this is a great liming source. It says it's a great liming source. Calcium carbonate will readily dissociate in soils and replace the free hydrogens and aluminum on exchange sites. And this is the final product. Calcium replaces hydrogen in this example, and that reacts with the carbonate to form CO2 plus water. There is no acidity on the right-hand side. It's gone. And we replaced the hydrogen with a base, which increases something called the base saturation of the soil. What about calcium chloride? What if you had a lot of this laying around? Would it be worth using as a liming source? No, it's not a good liming source because it fails to neutralize. This is the reaction. You have the clay with two hydrogen ions on it, and you add calcium chloride. Calcium is going to kick the hydrogen ions off and replace it with calcium. And what's left? What can hydrogen react with? Hydrogen has nothing else to react with except for chloride from the calcium chloride. And in fact, if you were to combine both of these, maybe you know what this is, HCl. That's hydrochloric acid. You've just generated acidity in the soil solution. There's no neutralizing the acidity. So this is a poor liming source. Now, what about this option? Sodium carbonate. It's not a good liming source because sodium is not beneficial for plants, but it does neutralize acidity. So here's the reaction. It's exactly like calcium carbonate. The sodium from sodium carbonate replaces the hydrogen ions on the exchange sites of clays, as you see on the right-hand side of the equation, and the hydrogen ions react with CO2 or CO3 to form carbonate CO2 plus water. It's the same reaction as in letter A, except sodium is being used instead of calcium. Now, I can tell you that when you have soils that have excessive amounts of sodium, sodium has a very large hydrated radius as compared to calcium, which is rather small. And when sodium is attached to clay particles, because of the hydrated radius, it pushes clay particles apart and causes soils to disperse, meaning the soil doesn't have much structure, it could be structureless, and the pores are closed because the sodium is pushing the clay particles apart. And so that reduces infiltration, aeration, percolation, etc. So this is why we don't use sodium as a liming source. In fact, adding sodium to soils is a bad idea. So let's talk about one other example here. What about gypsum? Oftentimes people have come to me and said, hey, Jim, can I use gypsum as a liming source? And I would tell them no. And this is why. So gypsum is simply calcium sulfate. And when calcium sulfate dissociates, there's no effect on pH, right? What is going to affect pH here? Nothing, right? There is no carbonate to react with any free hydrogen ions that are kicked off the site. And in fact, if hydrogen ions are kicked off the site, the exchange sites, and it reacts with SO4, it forms sulfuric acid. So, okay, there's two examples here I want to share with you. But if calcium exchanges with aluminum on exchange sites, the pH actually decreases in your soil because of the formation of aluminum hydroxide, gibbsite, which is a mineral, and the creation of 3 free hydrogen ions in the soil solution. So the pH can go down if you add calcium sulfate to soils that have high amounts of aluminum on the exchange sites. What about iron? Okay, in iron soils that are rich in iron oxides, these are highly weathered soils. What happens? In these systems, the sulfate can actually react with iron and iron hydroxide, right? These are highly weathered soils that you would find in like tropical locations or in Florida. And you might form iron sulfate as a mineral. And what comes off of this formation? OH, hydroxide. That actually increases the pH. So the bottom line is that gypsum effects on soil pH vary, and it's likely not a good idea to use gypsum as a liming source. Stick with the liming sources that we're going to talk about in one of the next videos.